So now we're switching gears and moving into the start of the Fracton session. So we're going to start off with a talk by Chen from Caltech.
Yeah, thanks, Jen, and thanks for everybody for staying and for coming. So like Jen said, this is the start of a Fracton session, and Mike and Yongbak will give more talks in the afternoon. And this will be, well, especially my talk will be a shift from the previous talks of this morning, because this topic of Fracton, at least when it started, it's a bunch of very toy models, and I often get asked of how to relate it to experiment. So this talk about Fracton and Chern-Simons theory is, well, I did the best I can, and one attempt of connecting it to maybe something that that's closer to experiment, or maybe something that potentially can be connected to experiment. But I'll try to explain why we can think of Fracton, this very new, very exotic thing in terms of Chern-Simons theory and how that's connected to maybe some quantum Haah physics. All right, so let me just jump right in. So Chern-Simons, of course, these are mathematicians, and decades ago they proposed that there's some very nice looking topological terms. I'm not explaining what that is, but this very simple form of Lagrangian terms leads to some very exotic and very useful physics. And the slightly complicated form contains more, because we can have, you can imagine there are multiple fields, and these fields, they can mutually have these Chern-Simons term. And then the key thing is that the coefficient characterizing their Chern-Simons interaction is given by this symmetric integer matrix. And that's the key thing I'm going to build around and then extend to 3+1D to talk about fractons, because originally this Chern-Simons theory using 2+1D or 3D, people just talk about space-time together, but we want to extend it to 4D or 3+1D. Okay, and of course this Chern-Simons theory in 2+1D is very well understood. It's been decades, and some of the very nice connection to physical system is through simple examples like if k is equal to 1, the simplest case you can imagine, this corresponds to the physics of integer quantum Haah. And if k is equal to 3, this corresponds to the simplest fractional quantum Haah of mu equal to 3, mu equal 1/3. And then if k is a slightly more complicated form of 0, 2, 2, 0, where it is still symmetric and integer, this corresponds to Z2 gauge theory, or what people call the toric code topological order. So as I said, the matrix K captures everything, the most important universal properties you want to know about these 2+1D topological states. For example, the determinant of the matrix gives us the ground state degeneracy on a torus. And then the inverse of the matrix gives us fractional statistics and fractional charge. So all we need to do is just take the matrix and do some calculation with it. For example, if k is equal to 1, and then there's not much, right? The inverse is also equal to 1, which is saying that the excitations are just electrons. And if it's if k is equal to 3, then the inverse is 1/3, so the excitations are 1/3 of an electron. But if it's a matrix of 0, 2, 2, 0, then the determinant is 4, it's -4, but it's 4, corresponding to a 4-fold degeneracy on torus. But then the 1/2 in the inverse of the matrix gives us the mutual braiding statistics of a Z2 charge and a Z2 flux. All right, so that's very well known in 2+1D. But then, as I said, we want to take it one higher dimension to go to 3+1D, because this is where fractons were originally discovered, and we want to make connections to that. Of course, I haven't said what fracton is. I will say that in a few slides. So in order to take this Chern-Simons theory to one higher dimension, it was famously known that somehow this particular form of topological term works in 2 plus 1D, but there's not a very natural generalization to 3 plus 1D. But the way we are trying to add the extra dimension is to say, okay, let's still keep these A wedge dA term and still keep the A as a 2 plus 1D field, but instead we can have many, many, many of them. So we can have infinite number of copy of these A's, and we imagine that they line up in the third direction. And that's what gives us the extra dimension. Okay, so we imagine that these I and J, they take value not just from 1 to 2, but among all the integers, all the negative integers and all the positive integers. And so that gives us the third direction. Okay, so and let's just consider the simplest example we can have. For example, this K matrix now with this infinite extension of the index, it becomes an infinite dimensional matrix, right? It's just a huge matrix. And then the simplest kind of symmetric integer infinite dimensional matrix, we can imagine that one of them takes this diagonal form where you have a bunch of 3 on the diagonal and then nothing or just all 0 on the off diagonal. And of course, this physically, this corresponds to the very simple, well, theoretically simple picture of having a bunch of fractional quantum Haah and then just stack them up. Because this Chern-Simons term is diagonal, meaning that each copy of the A field only coupled to itself, right? It doesn't talk to all the other fields. So we just have one copy of fractional quantum Haah, another copy of fractional quantum Haah, not talking to each other at all. So theoretically, at least I can just imagine that I take all the layers and stack them up. And experimentally, I know it's still hard to realize. But, so just this is the most simple and straightforward way we can try to extend this Chern-Simons theory to 3 plus 1D. And we can observe that immediately that there's something non-trivial about this model. For example, if we consider it as a 3-dimensional model, 3 plus 1D model, and we calculate ground state degeneracy on a 3-dimensional torus, imagine a periodic boundary condition, then the ground state degeneracy goes exponentially with the number of layers, because of course each layer has a ground state degeneracy of 3. So if you stack them up, you multiply the ground state degeneracy. And then the fractional point excitations move in the xy planes. And they only move in xy planes because the layers, they're just decoupled, so they don't hop from layer to layer. And we have something called the planar excitation. This is, of course, you will say, well, this is, of course, how it should be because it's a stack of 2D layers, right? But if I didn't know that this material has a layer structure, a decoupled layer structure, but rather I just treat it as a 3-dimensional box system, it actually looked quite surprising, because if we think about a gapped bulk topological order in 3 plus 1D, the usual picture we have is very different from this decoupled layer. For example, we can have a Z2 gauge theory in 3 plus 1D, and it's gap, and there's some fractional excitation, and there's a point excitation, and there's a loop excitation. And the point excitation, once you create it, it can move in the 3-dimensional bulk. It's deconfined in that sense. And then the loop excitation, it's a loop, and then the point excitation can go around the loop excitation. And then if we have periodic boundary condition, the ground state degeneracy is 8. The ground state degeneracy is a finite number which doesn't change with system size, not to say go exponentially with system size. So this is very different from this stack of quantum Haah. But then if we actually talk about fracton compared to some of the earliest fracton models that people propose, there's actually more similarity to the fracton models. So let me just jump to some of these fracton models, and without getting too much into detail, tell you roughly some of their most prominent features. So one of everybody's favorite example of a fractal model by Saga, Zhou, and Liang proposed in 2016 is this XQ model, which is a lattice model defined on a cubic lattice and with some Hamiltonian all commuting with each other. And the nice thing about this model, of course, it's not that it's experimentally easy to realize. It has this 12-body interaction, but rather that all the Hamiltonian terms commute, so we can do exact calculation about its property. For example, the ground state degeneracy of this model, the log of the ground state degeneracy is like 6L minus 3, where L is the linear size of the lattice. So it grows exponentially. The ground state degeneracy grows exponentially with the linear size of the system. And then there are different types of fractional excitations. For example, we can apply a string of sigma x and create excitations at the two ends. And we can do so in all three directions, in x direction, y direction, and z direction. But what happens is that the excitation created in this way, in the three directions, they're actually different from each other, meaning that we can only separate a pair of excitation in one direction, but not try to drag them in the other direction, because if you try to drag it to the other direction, it changes type. It changes from the purple-red to the purple, actually purple-green. And something has to be left at the corner where you try to turn. So this is why people call this a dimension 1 excitation. And this is not even a dynamical constraint. This is just fundamental constraint saying that these quasi-particles, they can only move along a line. Otherwise, there will be something left at the turning point. And then another type of excitation, now we're using the word fractal, is what people call the fractal excitations. And the fractal excitations are made by applying some different operators, generating excitations at the corner of a rectangle. So you can see that we're generating 4 excitations at the corner of a rectangle. And these excitations, they're called fractal excitations because for these ones, you can't even move them in any direction individually. So if you just see a single excitation sitting in space, there's no way to just take that one and move it somewhere else. So these kind of point excitations are fundamentally different from all the particle or quasi-particle that we're used to. Okay. And of course, then if we make a pair of them, if we have a pair of fractals or these pair of dimension 1 excitation, they actually move in planes and they become the planar excitations. And actually, couple years even earlier than that, Zhou proposed his very famous Haah code, which is another cubic lattice stabilizer model, everything exactly solvable, but again, very ugly looking Hamiltonian. I won't try to explain what this Hamiltonian is, but it's a exactly solvable Hamiltonian. And then he can calculate also these type of properties for this model, and his model is even more exotic. His model has some kind of hidden fractal structure inside it, and there's some very exotic property. For example, the ground state degeneracy follows this crazy formula. But if you look at it, there's also similarity to the XQ model. For example, if the system size is nice, meaning that if the system size is the power of 2, then the log of the ground state degeneracy goes like the linear system size, meaning that the ground state degeneracy is exponential in linear system size. So at this particular system size, at least the scaling of the ground state degeneracy looks similar to the XQ model. And then Zhou also analyzed how excitations can be made. It turns out excitations are created 4 at a time, and they are separated like through a process of fractal structure. Okay, so originally you can create 4 sitting at the corner of a tetrahedron, and then we can stack the tetrahedron to separate the corners. But then if we try to repeat that process, we start to to stack tetrahedron of tetrahedron of tetrahedron, and then eventually we get a fractal structure if you want to push all the excitations away from each other. So this is of course very exotic to Haah's code, but it is another example of where point excitations don't move on their own, but rather separate through a very complicated process. Okay, so we see that there's some, well, these models, they look crazily different, but they share some common properties. For example, the ground state degeneracy grows exponentially with the linear size of the system. And also there are fractional excitations that somehow are not free to move in the full bulk space. Okay, so they're either restrained to move like along a line or restrained to move along a plane or not to move at all on their own. So for models that share these loosely collective similar property, now people call them fractals. Okay, and basically people try to phenomenologically divide them into types. Now there's a type 1 and type 2 difference, where the type 2 is the more exotic fractal type, fractal like Haah's code. But the type 1 involve, for example, the X cube, which loosely speaking doesn't have the fractal structure, and then there's some excitation that can move, maybe along a line or on a plane, but they can move somehow. Okay. So now connecting back to the Chern-Simons theory I was talking about, the reason we were thinking about the Chern-Simons theories of this form with a huge diagonal matrix, even though pictorially this looks very trivial, it's a stack of two-dimensional quantum systems. But if we think from the point of view of fracton, we can say that this gives us another example of fracton physics, because, well, we see that ground state degeneracy has this scaling, and also we have point excitation that move in XY plane only. So this is of course a rather trivial kind of fracton physics, but it's more connected to fracton than connected to the original kind of topological, conventional kind of topological order of, let's say, gap gauge theory. Okay, so we can put this diagonal Chern-Simons here. But, well, if it's just diagonal Chern-Simons, it will be too trivial. It will be kind of boring, right? We have just a stack of two-dimensional things. But the nice thing about this Chern-Simons formalism is that if we go slightly further, we consider slightly more complicated matrices, we can actually go pretty far. Okay. So one of the example is to start from the diagonal case and then just add 2 lines of secondary diagonal. Okay, so let's say the diagonal is still 3, and the secondary diagonal, we put 1. And here's some periodic boundary condition that I just take. And everywhere else, we still keep the entries to P0. Okay. And actually, this is not something new. This is something people have studied starting from the 90s and 2000s, thinking about 3-dimensional fractional quantum Haah. So the picture is that if we start from this decoupled layers of fractional quantum Haah, and let's say we originally have the nu equal 1/5 layers and stack up. And originally they're very far separated from each other, and there's no coupling, and then we would have a K matrix with diagonal entry being 5, right? But then we imagine that we push these layers closer together so that the electrons in neighboring layers start to have Coulomb repulsion with each other. And because of the Coulomb repulsion, the electrons in neighboring layers would also try to avoid each other, introducing extra, these off-diagonal zeros into, if you write a Laughlin wave function, this will give you a Zi minus Zj kind of term in the Laughlin wave function. So people try to model these kind of coupled fractional quantum Haah with Coulomb repulsion with a matrix like this. And once we write down the matrix like this, people immediately realize that there are some amazing properties associated with this matrix. For example, as I mentioned, the key feature associated with the matrix, this K matrix is given by its determinant and is given by its inverse, right? for example, if we calculate the inverse of the matrix, it turns out to be very complicated. And this is a 7, I think this is a 7 by 7 matrix that I try to take a inverse. And if you make it bigger, it will look even more complicated. And you see that there's a huge denominator, and then the entries is non-zero everywhere, and it's decaying in some way. And if you make the matrix bigger, it just starts to have even more bigger denominator and more complicated entries. But what this means is that if we take the limit of infinite system size, something amazing shows up, and something amazing is some irrational numbers. Okay. For example, we can ask in this integer, in this quantum Haah setting, we can ask if we insert a flux in one of the layers, and then the flux in another layer, creating quasi-particles, and then we try to braid them around, what is the braiding statistics? And the braiding statistics turns out to have some irrational number in it. Okay, so this is I and J are the layer number. So if you have in I's layer and the J's layer, two particles, two fluxes going around each other, it's given by this pretty crazy irrational number. And moreover, we can calculate the determinant of the matrix, which is not something very straightforward to do. And it turns out the ground state degeneracy given by the determinant also has some association with irrational numbers. Of course, if you calculate for any finite layer, it would be an integer. But if you take the limit of the number of layers going to infinity, then we can separate out the terms and only keep the leading term in the scaling of the ground state degeneracy. And that gives us this exponential, but the base of the exponential is an irrational number. And then we can talk about, well, what's the whole group of quasi-particles, because the quasi-particles should form a group. And the group formed by all the quasi-particles, the flux that you insert in every plane, looks also crazily big. It's given by the product of two cyclic groups, and the cyclic groups have huge order, meaning that each generator is very fractional, and the order has to do with Fibonacci sequence. Okay, so these are just features that's never seen if we take a 2+1D Chern-Simons theory and with a finite layer of fields and then couple them. This only shows up if we start to couple them in an infinite way. All right, so this so-called tridiagonal Chern-Simons, it also has these fracton feature, right? Because, well, the ground state degeneracy goes exponentially big with the number of layers, with the height of the system, and there are some quasi-particles that move in planes, but then the statistics is irrational, and the planar group is crazy. So it looks very different and very surprisingly odd in a way compared to the X cube and the diagonal Chern-Simons. And there is indeed a very concrete way where we can try to formulate their difference. And this has to do with what we have been playing with in the last couple of years, an idea called foliation. Okay, so let me just try to take some time to explain to you what this foliation idea is about and why this tridiagonal Chern-Simons theory is so different from the diagonal one, also from the XQ model. Okay, so this idea of foliation has to do with how we imagine we grow a system with fracton order. So usually when we grow a crystal, we throw something into, okay, it's my elementary school level of growing a crystal. We throw some seed into a solution and then the crystal grows, right? So you need to have something in the solution that attached to the seed, and then you grow the crystal. But then for these fractal model, what we need in the solution, what we need to float around in order for the crystal, for the system to grow, is actually something highly non-trivial. In particular, in this case of XQ model, if we want to grow the system by one layer in the z direction, from Lx times Ly times Lz to Lx times Ly times Lz plus 1, we need to add a layer of this two-dimensional toric code. So two-dimensional topological order, two-dimensional Z2 gauge theory. So what we showed in this paper is that you can stack this two-dimensional layer onto this three-dimensional bulk model, and then we can do something called smooth deformation, so that the model actually becomes slightly bigger. Okay, and this is saying that well, we can use this method to grow the system bigger. We can also use it to make the system smaller, right? If we start from a bigger bulk, we can do this decoupling process and take out one layer of toric code, another layer of toric code, another layer of toric code. We can take a lot of layer of decoupled two-dimensional topological order. So this already immediately captures a lot of the non-trivial feature that we see for this particular 3+1D fractal system. For example, well, we mentioned that one key feature is the scaling of the ground state degeneracy with the system size, the exponential scaling. And that's already obvious from this foliation picture, because we found that with smooth deformation, we can just peel off these two-dimensional toric code layers. It's like taking one layer off, another layer off. So there are lots of hidden toric code layers inside the three-dimensional bulk, and because each layer would contribute a ground state degeneracy of a factor of 4, so when you stack them up, that gives you the scaling, the exponential scaling of ground state degeneracy. And then it's also natural to have so-called planar excitation moving inside the fractal model, because these toric code layers, they come with their own anyons. They're two-dimensional topological order. They have fractional quasi-particle moving in their plane, and when we insert them into a 3D bulk like that, they keep all their, the smooth deformation keeps all the universal properties of the 2D layers. And with that idea, that gives us the idea that if we want to compare three-dimensional fractal model one with another, maybe we should be more relaxed regarding what we consider essential and what we not consider essential. Of course, this is one way to formulate things, and actually I think Mike is going to talk about some related but maybe slightly different way of considering fractals in the afternoon. And there are different ways to, we can try to formulate things, and given these different ways, we can actually come up with different classes of different classification schemes of fractal order, and try to understand what is essential to fractal physics and what is essential to so-called universality of fractal models. Right. So in this foliation way, what we choose to do is to say, okay, we should consider all these 2D topological order floating around. We should consider them as coming for free, free lunch. And if they're just floating around in the environment, and we can just add them freely into the system, then when we're comparing the 3D fractal orders, we should somehow mod out the contribution coming from these stack of 2D layers, but consider something that's still non-trivial, even when we mod out the decoupled layers. Right. So this is how we try to make sense of what it means to have a fractal order and what it means to have a fractal phase, and how to compare fractal order between different models. So we're modding out contributions coming from 2D layers, the excitations, the entanglement, the ground state degeneracy, but then comparing the feature that is still there even when we take all the 2D layers out. So in this case, in this sense, the diagonal Chern-Simons theory that I started from, which is a pure stack, effectively a pure stack of 2 + 1D fractional quantum Haah, would be considered a trivial fractal order because, well, everything's captured by the layers already. But then we can also try to come up with non-trivial examples. For example, this is a case, this pattern of 0, 2, -1 and repeated indefinitely. This infinite dimensional K matrix is one that we came up, which does share this foliated structure as the XQ model. So to see that, we take the inverse of the matrix, and that you see that this inverse of the matrix is very different from the tri-diagonal one because the entries are still very concentrated along the diagonal. It's not everywhere. And this one, it doesn't lead to irrational numbers. It doesn't lead to Fibonacci number. It's much better behaved. And in particular, we can show through manipulation of these K matrix that the model described by this K matrix also has a foliation structure similar to the XQ model. In particular, if we want to grow the system size by 1, we need to add something called a Z2 cross Z2. I think this is a twisted gauge theory, and then do something in terms of the Chern-Simons formulation, and then we get a system of one size bigger. And similarly, if we want to go back, we can also do the decoupling of layers and layers of this twisted Z2 cross Z2 gauge theory. But then we see how surprising and how out of box this tri-diagonal K matrix is because the scaling of the ground state degeneracy with an irrational number that can never be accounted for by adding some decoupled 2D layer, because decoupled 2D layers don't have ground state degeneracy that's given by irrational numbers. And also this irrational statistics that can't be, because all the statistics we see in 2 + 1D are like 1/3, 1/2. It's never some irrational number like this. And also the fusion group cannot look like that. So because of that, we see how this a tri-diagonal Chern-Simons theory, even though it still doesn't have a fractal pattern, it still belongs to type 1 fractal in that sense, but it's a very different type of fractal model compared to the diagonal Chern-Simons, the X cube, and also the other foliated Chern-Simons theory that I showed you. So this is just showing how the Chern-Simons theory gives us a bunch of very different examples within the fractal framework. How much time? Okay, so but let me just very quickly go through the second part of very quickly about the Gapless version of these infinite Chern-Simons. And so if we actually tweak the entries in the K matrix further, we can get not only gapped examples, we can also get 3 + 1D Gapless examples, which also show some interesting feature, which is a more recent work by me in collaboration with Xiuqi and Haah. So basically what we realize is that, if we have the diagonal being 3 and the secondary diagonal being 1, or the other examples, these are all gapped. But then if we make the diagonal smaller, then we can actually have gapless cases. And the calculation of the spectrum is actually very easy. You just diagonalize the K matrix. And there have, so Amon and Joe and Arpid, they have a paper about, I think this one's published. They have a paper about these gapless cases and their anomaly and how they can come about from the coupled wire construction. And me and Xiuqi and Haah, we had another paper about Let me just skip all these and say something in conclusion. Yeah, the first thing we observe, which is actually also something that's observing Meng's paper, is that this is a stable gapless 3+1D model that we don't see a gauging variant local operator then actually allow us to open a gap. Because this is surprising because in 2+1D, if we have a gapless Chern-Simons, I don't want to go back. Okay. If we have a gapless Chern-Simons, usually what happens is that we can, it gets gapped out. And usually it means that there's some U1 symmetry that gets broken and then explicitly broken, so the theory gets gapped out. But in this 3+1D case, the operator that we can attempt to add to open the gap becomes non-local in the third dimension, and that's why it actually becomes a non-local operator, so we can no longer add them, and that leads to the robustness of the gapless spectrum of the system. But then on top of this gapless background, what we observe is that there's some interesting still topological feature remaining. For example, the point excitation are still deconfined, so we can still move them around. And once we move them around, we observe that there's some remaining topological feature. For example, there's some converging, in a sense, statistics between the point excitations. So I'm not claiming that this can be measured in experiment. I'm just saying that if you do the Chern-Simons calculation, there's some configuration where we can do the calculation such that we get a converging phase. Okay, I don't want to go too far claiming the experimental indication. All right, so that's all I want to say. What I try to show you is how we try to generalize the 2+1D Chern-Simons theory to 3+1D by taking an infinite number of these Chern-Simons fields and then sum them together. And we see that what we managed to do is to get some very interesting examples. We can get type 1 examples, we can get foliated examples, we can get non-foliated examples, and we can also get some stable gapless examples. And we were, well, Haah were able to find a continuous field theory description for the gapless case for when the gapless point has a linear dispersion. Okay. And of course, there are a bunch of open questions because this basically provides us another tool to look at fracton. It used to be that we played a lot with lattice model, and lattice model is very powerful, but very quickly get very complicated. And there's only so much we can do by thinking about lattice models. So this Chern-Simons theory, it effectively reduces a 3+1D problem to 1+1D, right? To a big matrix. So hopefully there's more we can do by just playing with this infinite dimensional matrix. But on the other hand, usually when we think about infinite dimensional matrix, we think about, let's say, hopping model of 1+1D electrons. But this model, which has been completely classified, and you can do pretty much everything with it. But the non-trivial thing about this problem, and also the interesting thing about this problem, is that the matrix we are looking at are integer valued, and they're symmetric. And because of that, their classification is very different from the usual Hermitian hopping matrix, let's say, describing electrons in a one-dimensional insulator or metal. So, for example, we can ask the equivalence class of these matrices in terms of this foliation idea. If we insert something and mix the orbitals, not orbitals, mix the fields in some way, how do we get equivalence classes of foliation models? And then for the non-foliated one, we have even less idea what's going on. For example, how do we grow the system size? We don't even know that. We don't even know how to in a sense, meaningfully think about renormalization transformation where we change the system size. And then these Chern-Simons theory, maybe we can use them as building block to build up some model like X cube where we have fracton excitations and dimension 1 excitations, and finally the connection to experiment. Maybe there's some. And that's all I want to say. Thank you.
I see. Thanks, very nice talk. So in this tridiagonal K matrix example, to try to create some excitations by acting with a local operator, do you create a finite number of these anyons, or do you need to create an infinite number of these anyons?
Sorry, what?
If you act with the local operator somewhere to create some anyons,
Yeah.
do you create an infinite number of anyons or just a finite number of anyons?
I think it has to be like if it's finite, then there's some.
Is there a single antiparticle for one of these?
I need to think more carefully, but my first intuition is that so all these excitations, they have very long tails.
Yeah.
They have a exponentially decaying tail. So if you only act locally, I would imagine that it has overlap with each one, but with a decaying overlap. So it could be that it just overlaps with this one, but then decays over distance. So if you literally want to say how many, then it's probably
okay. So it's,
that's I need to look at it, but
so the spectrum of this excitation will look very, very, very weird.
Yeah.
Maybe this is a related question. So in here.
Oh, okay.
In 3D, when you have point-like particles, exchange statistics can only be bosonic or fermionic. And you have these very strange exchange statistics for objects that you attributed to certain layers.
Yeah.
So is there something which is a line-like excitation, and did I understand this? Or?
Yeah, great point, great question. So, so first, I agree with you that if you have a fractional excitation that moves around in three-dimensional bulk, then it can only be boson or fermion. That's definitely true. Okay. So, but for fractal system, the picture we have is that there are particles that don't move in the full bulk. It's somehow confined to move in a plane. And in that case, it basically reduces to some 2+1D anion statistics, which can be more fractional than just boson or fermion. It can be some rational number. But this is not even rational number we're talking about. We're talking about irrational number, and which doesn't show up in 2+1D. So this is I'm talking about point excitation moving in a two-dimensional fashion, but their statistics are like irrational numbers. And the reason that can happen is related to what Santi was asking me. So if you insert a flux in one of the layers, in quantum Hall physics, what happens is that you accumulate charge. Right? The flux will accumulate charge. But it will accumulate charge in all the other layers, and the amount of charge accumulated throughout the layers decay exponentially. So starting from this layer, it decays exponentially as it goes away from that layer, but it's never zero. And in the limit of the system size being infinity, then the charges accumulated on other layers become irrational numbers. Okay, so of course, this is theoretical calculation. How relevant that is to experimental measurement, I don't know. But yeah, that's how you can get statistics as weird as that.
Hi, thanks for the nice talk. Kind of following up on a previous question and on the tail of your slide. So if we move away from exactly solvable models and into the regime of experiments, if there are excitations which are smoothly connected in some way to fractons, can you say anything about how they would be distinguished from other more trivial excitations?
Oh, how to experimentally probe fractons? How do we know that they're fracton systems? For example, if a particular material has
for instance, if I pump heat into the system, is there a signature in specific heat that I should look for?
Yeah.
Or
definitely. So this is There are other, well, there are better experts on that than I am, but I know that people have proposed, like Rahul at Boulder, they have done quite some work on that. Because basically what happens is that for these fractal systems, the excitations, they don't move as freely as you would expect for the usual 3D bulk material. So that leads to all kinds of feature in their thermalization processes or diffusion or all these kind of dynamical processes. So they're proposing like some non-diffusive dynamics or the coefficient changes or the power changes. Yeah, all those things can be used to diagnose the existence of fractals.
Hi. So my question is related to Senthil's question, I think.
Okay.
So for this tridiagonal K-matrix theory, I'm wondering what happens if you take a planon and you keep fusing it with itself. In particular, you know, because the fusion group only has these two very big factors, I would think that what would happen is the spatial support of that excitation will have to change in some non-trivial way.
Exactly.
Like, does it spread out or does it move, or like, what do you know? Do you have any understanding of what happens if we do that?
Yeah. So the fusion group has exponentially big order. So if you just take any element and you try to fuse it with itself, then you need exponentially of them to get back to identity. So so basically, I can imagine that, yeah, as you fuse a particle with itself, it starts to, I need to do some calculation about it, but basically, you imagine that it would still get these exponential tails, but then still have this very weird feature maintained up to very big order. So no finite, if you just fuse finite number of them, not much will happen.
Thanks.
Hi, Xie. Do you know what happens in these stacked Chern-Simons cases? You can usually naturally couple them to a gauge tool for translations. Do you know what happens if the system is, especially in the non-foliated cases, sensitive to dislocations, for example?
Oh, yeah. This is a great question, because back in the days, the 90s and 2000s, when people look at these, for these papers, when people think about them, these papers, they talk about the whole phase diagram, and they talk about potential instabilities in these phases. And one possibility is to break the translation symmetry in the z direction, and they call this staging. So basically, you can imagine all the electrons go, for example, all the electrons in 3 layers go into 1 layer, or maybe here 5 of them go into 1 layer and become an integer quantum Haah. So break translation symmetry and get basically some other phases. So so I think you are asking about the Gapless case, right? Because the gap case, you can potentially drive a transition, but that's not a relevant.
Yeah, I guess I'm asking if in the Gapless case, if those systems can be thought of as some kind of generalized topological semimetal, right? Where you have, like, if you stack Chern-Simons, you couple them strongly, in the free case, you get wild semimetal, right? So yeah. I'm asking if these Gapless cases are like that.
Yeah, so in the Gapless case, sorry, where is it? In the Gapless case, basically, we also consider the situation where translation symmetry can be broken, but eventually we convinced ourselves that this is not like a instability, in the sense that, for example, one way we can very explicitly break translation symmetry is to add something here. So this is the Chern-Simons term, and this is the Maxwell term. Okay. And there's no way we can perturb the Chern-Simons term, because this is integer matrix, so there's no perturbation to that. But for the Gapless one, well, for the Gapless one to be well defined, we need to include the Maxwell term, And the Maxwell term, we can more freely change its parameters. And we can try to, let's say, introduce translation symmetry breaking into the coefficient of this term. But then the key feature is still captured in the K matrix. So the universal topological feature, and especially the gap of this model, is still determined by it's the spectrum basically of K divided by the spectrum of this matrix in front. So this is just in the denominator. So basically saying that if this one goes to 0, then as long as it's divided by some reasonable number, then the ratio still goes to 0.
Okay, thank you.
Yeah.
Okay, I think we should thank Chia again.
Yes.
Thanks, Chia.